What if we have a car that's driving around a circular racetrack, but it's intended for very high speed races? Okay, so we have this car, it's going in this direction, and it's intended for very high speed races. Okay, now one way you can do that, as we saw in the last video, is you can just maybe increase the frictional coefficient between the road and the rubber tire. Okay, and that's in fact something what they do is they have the tires for high-speed cars are very smooth, so they have a lot of surface area to grip the road. But a simple way, and this is also employed not just in racetracks but in curves on freeways, is banking it. Okay, so from a top view, I can't tell the difference between that and just a normal circular track, the horizontal track. But a banked track, if I were to look from behind, so I'm going to take a back view here. I'm going to look from behind. The track is angled with respect to the horizontal by some angle. We call that the banking angle. Okay, so banking basically means instead of having the road flat, you bank it so it's the outside curve is coming up towards the center of the track. So the car, if I'm standing right here looking at the car, I see the car is actually running around this curve at an angle, okay, and so it's moving around this curve, but it's at an angle now. So the question is, how does that help? Why does that help? Now, the first thing to observe is that friction's still at play, okay, but now the normal force, which points normal to the road, before with the horizontal road it was straight up and had no radial component. Now this normal force is pointing this way and it has a radial component. So we're going to need to draw that to make that clear. So I'm going to draw, you might think I want to draw, it looks like an inclined plane, so I might want to draw a tilted coordinate system, but our acceleration is not downwards, it's still straight into the center of the circle, so it's still horizontal. And so I actually still want to do a horizontal and vertical coordinate system, with this being the radial direction pointing straight to the center of the motion, okay, and this being y pointing straight up and down. So with those two, identifying these forces, well, gravity is going to point straight down. Okay. The force of gravity is pointing straight down, so it's in the negative y direction. My normal force is going to be pointing something like this. All right? And I'm not going to try and draw these perfectly accurate in terms of sizes because it's going to get a little complex, but we'll kind of focus on qualitative directions and sizes and then let the math really specify. Okay, so this is going to be the normal force. Now something that's important is if I were to look at this and draw that cross right there, and then look at a horizontal cross, I'm going to go like this and like this, so just not a cross but just two lines. We can see that if the angle of inclination is measured right here, then this also must be that same angle. So the normal force on a banked road makes the angle theta with the vertical if the angle is the banking angle, which if by definition that's measured from the horizontal. Okay, so from that we immediately get a horizontal component. Oops, put an X, I should put an R here as my radial component, and then we get a vertical component. Alright, and this horizontal component would be opposite that angle. I can move this up here, and so this would be n sine of theta, whereas the vertical piece would be cosine. Okay, now that helps us digest the normal force component. The first thing to notice is part of that normal force is pointing inward, helping to contribute to an inward acceleration. Okay, but to make this most general, we can still include friction. There's still friction between the tires and the road. Now that, if there were no friction, this car would want to fly outward, mostly. Now I'll talk about another example where maybe that's not true, but But generally, if we're trying to go really fast, then friction is helping us keep us in. And if there were no friction, we'd slip out. Okay? And so that's going to be down the road, which is 90 degrees with the normal. So I'll just go and do that. So this is going to be friction, and this is that static friction. It's what's keeping the wheels from slipping. And it has, the angle it makes is theta here, which gives a piece downward like that. And I'm going to draw the other piece here because that's a little congested there. I'm going to draw the other piece here. So this is FSR, and this is FSY. Okay? Alright, so with that, then what we have is our Newton's second law for both directions. We have now three vectors in the y direction. That's going to relate the normal force and this downward frictional force to the force of gravity. And we have two vectors that are contributing to the radial motion, the radial acceleration. Now, if this car is not accelerating up and down, we know that these three must sum to 0. Let's go ahead and look at that right now. Y, I'm going to choose, I've chosen up to be positive. I'm going to F net Y equals MAY, and the car's not jumping up and down, so that's 0. So what is F net Y? I have NY, which I'm going to, for brevity, go ahead and plug in NY is N cosine theta. Okay, so that's my upward force. And I have these two downward forces. I'm going to have mg, the gravitational, and then minus this FSY. Okay, now we don't know what that is quite yet, but we can come up with some limiting cases where we can go further with this. So I'm just going to put Fs, and Fsy would be sine of theta. Okay, and that must equal 0. Okay, so now right now I don't know N and I don't know Fs yet, but this is at least a relationship that relates those with the gravitational force. Okay, now let's look at the x. See what we get from the x. So the x, I have F net x, my bad, R. Let's look at the R. F net R equals MAR. Okay, and that is not 0. In fact, we know that that is mv tangential squared over the radius of this curve. So there will be explicit, that's my tangential velocity, and the radius of this curve is r. Okay, so now I've taken care of what I know about the acceleration, the kinematic side. Let's go look at the dynamics of the forces. If I look over here, I have n sub r, and that's going to be this side, so that's going to be n sine of theta, and then this was pointing in also, so plus Fs, and that's going to be adjacent to this theta here, so that's cosine of theta equals mvt squared over r. Okay, so I basically have two equations with two unknowns, this normal force and this frictional force. Not sure what they are. Now, I could measure the velocity, or I could ask, what is the velocity? To do that, then I'd have to know some information about either the normal force or the frictional force. Now, here's the cool one. It's like, what would that banking angle have to be so that just the normal force is sufficient to allow for this speed? Okay, well, so there's going to be some speed that we're driving at. So we'll suppose we know this speed, and we want to say, well, what does the banking angle need to be so that the road could be frictionless? So if it was icy, and you could still drive around this curve, and the normal force component alone is sufficient to achieve that radial acceleration. Well, that just means that the term with the frictional force goes away. Okay, and so there'd be no frictional force here either, and the normal force is the only force that's going to contribute. So we can then, if that's gone, we can find the normal force here, plug that in here, and then we can solve for the angle and find it that way. But a fun one is, what is the maximum speed we can go now for this one? And if we ask that question, then Fs is no longer just this kind of variable force that grows with the applied force, it becomes Fs max. Or in other words, we're going to reach some speed that we go just barely above it, we slip. And that's the definition of Fs max. And so in that case, if we asked a question like that, then we just can replace this, Fs max, with what we know, Fs can become Fs max, and we know that that's equal to μs times the normal force. Okay. Now, the thing to be careful is that's not the normal force in the vertical direction or the normal force in the horizontal direction. That's the total normal force. It's the normal force. The frictional force is dependent on the full normal force. So by plugging that in right there, we suddenly have reduced this, and we can now find this maximum speed by first finding the normal force from this equation, plugging in here, and then finding that maximum speed. Okay, to finish off this discussion, again, I've done the process, haven't really done any specific results, but you can see what directions you can go with it. Here's a really cool scenario, and this is a friend told me once, is they were driving through a big city in this crazy set of freeway interchanges, and it was raining ice. It was freezing rain, and as my friend was coming towards a large curve in the freeway that was banked, it was a banked curve. Everyone was driving slow. They're driving slow, and so because it's ice, you don't drive fast on ice, right? And he was coming towards this bank, and it was kind of a downhill, and he could see that there were a whole bunch of cars piled up on the inside of that curve. So down here, they're all piled up down here. And he saw that and remembered a physics course he had taken about this type of problem. And he remembered that there's a particular speed at which you can drive so that you can make it around the curve, and it's not driving slow, it's driving such that this goes to zero. And so he actually drove a little bit faster than he was going on the straightaway. He drove faster. That allowed him to let the normal force have him go all the way around, and he didn't slide in, because if he drove too slow, then that frictional force was not big enough, and so the normal force was pulling him inward, and so he had to go faster to go around the curve. So I thought that was really impressive. I don't know if I could have even acted that quickly in a response, but it's really cool, the idea that you can use these things to recognize that that when you're driving around an embankment, it's not just friction holding it in, it's also the normal forces. So there's actually a minimum speed too that you can drive if it's on a frictionless surface in order to make it around that curve. And that's basically when the frictional force is zero and you utilize just the normal force.